Hey there, if you're a student staring down a dense electrical engineering textbook right now, just take a deep breath. You're in the exact right place. Today, we're having a calm, focused study session where we're going to demystify the absolute foundation of electrical engineering. We'll translate all those heavy, complicated concepts into intuitive, easy-to-grasp building blocks.
Before we even look at a single piece of math, I want you to just picture something for a second. Think about the device you're watching this on. Inside that plastic and metal casing are thousands of tiny pathways, all silently managing an intricate, invisible flow of energy. But what is literally happening inside those wires?
To keep things from getting overwhelming, we're going to look at circuits like a board game. First, we'll figure out our currency, charge and current. Second, we'll meet the playing pieces on the board. And third, we'll learn the unbreakable rules of the game.
All right, Act 1, the currency. Let's zoom way in. At the literal foundation of all this, we have charge. It's just a fundamental property of subatomic particles, right? Protons carry a positive charge, and electrons carry a negative one. We measure this electrical charge in a unit called coulombs. If we're playing a board game, imagine coulombs as your physical coins. You have to have these coins before absolutely anything else can happen in the game.
Now, don't let this calculus equation freak you out. I equals dq over dt looks intense, but it's really just describing speed. Current is quite simply the rate at which those charges flow past a specific point. If coulombs are our coins, current is just how fast those coins are being handed from one person to another, and we measure that flow rate in amperes. But here's the catch. Those charges, they don't just move on their own. For that current to actually flow, it needs a serious push. And that is exactly what electromotive force, famously known as EMF or voltage, comes in to do. Voltage is the electrical pressure. It does the physical work required to shove our charge from one place to another. Without voltage, your coins just sit there. So, what happens when we combine that push from the voltage with the flow of the current? We get power. Calculated as P equals V times I, power is simply the rate at which work is getting done in real time. And if we leave that power running over a period of time, we get the total energy, measured in joules. Think of power as how fast you're running, and energy as the total calories you burned on that run.
Okay, let's move on to Act 2, the pieces, the actual physical elements sitting on our circuit board.
You can basically divide everything in a complex electrical network into two simple camps. On one side, we have active elements, think batteries or generators. These are the powerhouses that actually supply energy to the circuit. On the other side, we have passive elements, like your phone screen or motor. These guys don't create energy, they just use it up or maybe store it for later. If you look at this handwritten diagram, it perfectly maps out our whole family tree of game pieces. See how it branches out? Active sources divide into voltage sources and current sources, and our passive pieces branch out into your standard resistors, inductors, and capacitors. It's really just a small handful of unique pieces that we use to build, well, everything. Another really cool way to look at these pieces is by how they behave when you actually push current through them. Linear elements are the predictable ones. They scale perfectly in a straight line. If you double the voltage, you double the current. Resistors do this beautifully. But nonlinear elements, like diodes, they play by their own complex curving rules. They might let current breeze through in one direction, but slam the door shut in the other. All right, we've got our currency, we've met our pieces. Now for Act 3, the rules.
This is the big one, the absolute most famous golden rule in all of electrical engineering, Ohm's law. It's beautifully simple. V equals I times R. It shows that the voltage, our push, across a conductor perfectly equals the current multiplied by the resistance. It's like a balanced scale. If you crank up the resistance and keep the voltage exactly the same, the current has absolutely no choice but to drop.
But reality check, even golden rules have their limits, which is super important to remember for exams. Ohm's law is fantastic for basic, linear conductors, like a copper wire. But when we start messing with advanced tech, like vacuum tubes or semiconductor devices, it completely falls apart. Remember those nonlinear pieces we just talked about? Ohm's law doesn't apply to them. That's why we need deeper rules. And that brings us perfectly to rule number 2, Kirchhoff's current law, or KCL. Simply put, the algebraic sum of currents meeting at a node, which is just a junction where wires intersect, is equal to 0. In plain English, whatever amount of current flows into an intersection,
That exact same amount absolutely has to flow out.
Check out this handwritten node diagram here. Think of it like a perfectly managed traffic intersection. The number of cars, or in this case current, driving into the center mathematically has to balance the cars driving out. So current I1 and I5 point inward, while I2, I3, and I4 point outward. They have to balance out. No electrons magically disappear at a stoplight.
And our final core rule is Kirchhoff's voltage law, or KVL. It's basically the sibling to the current law. KVL says that if you mentally walk around any completely closed circuit loop, the total voltage increases and the voltage drops will always perfectly cancel out to zero.
This sketch right here is a gorgeous example of KVL in action. We've got a voltage source, Vs, pushing energy into the loop, and 3 resistors, R1, R2, R3, taking little bites of that energy out, creating drops, V1, V2, and V3. KVL mathematically proves that the energy supplied perfectly matches the energy consumed. Vs just equals V1 plus V2 plus V3. It's a perfect closed loop of energy.
So if you're ever stressed out trying to solve a circuit problem, just take a breath and break KVL down into 3 calm, simple steps. First, trace a closed circle on the page. Second, mentally walk around that circle and note every component you pass. Third, add up the energy sources, subtract the energy drops, and set the whole thing to 0. Boom! It's not intimidating math, it's just accounting.
To really lock this all in, this diagram brings all the terminology together beautifully. You can see the branches, those are the physical pathways with our elements. You've got your nodes, marked 1 through 4, which are the traffic intersections where we apply Kirchhoff's current law, and you see the loops, labeled X, Y, and Z, which are the closed paths where we use Kirchhoff's voltage law.
Honestly, the coolest takeaway from all of this is a deep sense of peace about how circuits work. By just mastering these basic pieces, understanding the currency of charge, and knowing these 3 unbroken rules, you have the keys to basically any electrical system. Whether you're fixing a simple flashlight or analyzing a massive supercomputer, it is exactly the same game being played.
So, as you look at the electronics surrounding you today, your phone, your laptop, even just the lights in your room, remember this foundational idea. A massive, incredibly complicated network is really just a bunch of these simple little circuits connected together. It makes you wonder, if all this incredible technology is built on just 3 simple rules, what complex, overwhelming problem in your own life could be solved just by breaking it down to its basic fundamental rules?